Hello everybody, we're going to start talking about elimination and multiplication together. For matrices, this is a really important topic that you can look into. And let's get started. So we have here a 3 by 3 matrix with a b vector added on to the end. And we're going to do row reduction for this matrix. Doing so, we take the first row and we take 2 of it and subtract the second row, and we get the matrix on the right. Then we switch the third and the second row due to 6 being at the end. In doing that, we also have to switch that part of the b vector. Doing that, we can see 2 is aligned, so we can get rid of the 2 in the second row, doing row 2 minus row 1, and that gives us row 2. And thus, that gives us our upper triangular matrix. Using this, we can back solve with x equals. Then we get z equals -1, y equals 2, and then finally, last but not least, x equals 3. Okay, this is called row reduced form. So upper triangle matrix is a matrix A in the space R n by n. And after we row reduce, we get un of yen, which has the bottom being zeros and the upper corner matrix being all p's. If p1, p2, pn are non-zeros, then the rank of u is equal to n, which is equal to the rank of A. Columns of U are linearly independent. Rank of U is equal to rank of A in this case, since we are still preserving the column space. Row operations are doing that as such. If we did column operations, on the other hand, we would preserve the row space, but we're not doing that. And we only do this if A is non-singular. Non-singular means all the rows are independent. This is an independent matrix. Again, columns of U are linearly independent. And the column space of U is R of n. I think that makes sense, especially since it's a triangular matrix in R of n by n. U of x has a unique solution. That's literally the definition. And U is invertible. That's also part of the definition of being non-singular. So the goal is to figure out how to find the inverse of a non-singular matrix. And for that, we need to understand row operations as matrix multiplications. There's 3 ways we could do this. One is the column sense, which we already know. Taking 2 columns, A and E, multiplying it together, we take the columns of E. We take the columns of E. Remember that? And we multiply it with A. In doing that, we add them together, and we get our matrix. This is one way that we usually multiply. Second is via dot product. So dot products takes the row of A and the row of A2 and multiplies it with the column and column. Doing it as such, you can see that it gives us the same numbers. Finally, the third one, which isn't usually used as commonly, is row sense multiplication. This is kind of similar, but instead of doing A times E, we're doing E times A in this case. In doing so, we look at the columns and add it as such, and doing that, we get our solution. Does that make sense? This row sense is probably hardest, but I think the two new ones we've learned is dot products and row sense. So I'm gonna just do a little bit of a review. So three ways, let's just go over 3 ways we multiply is 1, via regular A times B matrices. We take the columns of B and multiply it to the rows of the whole matrix A. Multiply the whole matrix A. And what do we get in the end? In the end, we get an A, assuming that the matrix is n by n. Both of them, we get an n by n matrix. Okay. 2, for dot products, we use let's use this dot products. Okay, this one we take for each element that we're creating. For example, if we're going to the top right element, we take the first row and the first column. And with that, we go AE plus BG, etc. Let's just double check that real quick. You kind of see that happening here. We take the row, the column. And with that, we have that right here. It makes sense, right? Okay, part 3 is row sense multiplication. Well, something to note, either we take the full matrix of A from the first one, or we take the full rows. Second one, we always query the columns. Third one is row sense multiplication. This one's a little different, but in here, we have our A, B, C, D. We look at the rows. G, H. And then we multiply it to the columns, but in matrix form. What do I mean? Well, let's go back to our notes. We see over here, they multiplied the first row by the row and added it to the second row as well. So regardless of where we're multiplying, we're taking each row independence and adding it to each side of the matrix. So it's going to get a little long, but we're going to have A E plus F G, that makes sense, times the other two. Don't know why I looked. Oops, my bad. Taking AE times EF plus B times next column is GH. And this is not added. These are supposed to be braces, because these are technically like the rows or the columns. Vice versa, we do that the same for the bottom. That makes sense. Okay, going back to our notes. Elementary. Multiply F with A on the right. E will combine the rows of A. We expressed a row operation by multiplying A on the right with an elementary row, the elementary operation matrix. So the row sense is we switch the rows and called it. Call the permutation matrix. So when we switch the rows, it's called the permutation matrix. And this is a lower triangle matrix. This is the dot product sense. I think this is all we're going to do right now, but I'll see you in the next video. See you guys. Bye.